In this lesson, we're going to talk about how to do the same demo that we did in the previous lesson in PyTorch in Keras, thanks to a new library called TensorFlow Encrypted, which can allow you to do sort of the same style of encrypted computation with the TensorFlow backend as opposed to just a PySift or PyTorch backend. And this has recently been integrated into the PySift library, so it should hopefully feel very familiar in terms of the way that it's configured, just with a little of that Keras flavor. All right, so I guess the first thing I'd like to sort of mention is that there'll be this kind of the three steps. So we'll have train, secure, and query the model. We're going to take a model and we're going to MPC share it amongst sort of three different workers that are conceptually in the cloud, right? So it's encrypted between these different people who we trust to not collude with each other, and then we're going to be able to query against it. So for more information on the library itself, you can check out the TF Encrypted GitHub, as you can see, which is here. And then, of course, it's actually sponsored by Dropout Labs, which has done lots of work helping to integrate it into PySift as well. Great, so let's get started. So training a model in Keras. So the first thing we're going to do is actually just train a model sort of in the conventional way, right? This is just normal Keras training. So in the same way that we had kind of an example, normal training example, I believe. So this is training using MNIST data. We've got sort of a convnet with a few convoluted and pooling layers and some ReLU activations. So we're just going to train 2 iterations. So obviously we could train this more if we wanted to, but we wanted to be able to do it sort of in the context of this demo. So then we save this model to an H5 file, which is kind of the conventional way of saving TensorFlow files. And then what we're going to do next is we're going to hook Keras. So in the previous tutorials, you remember us sort of hooking PyTorch with a torch hook. This is exactly the same idea. It's taking Keras, it's adding in the new functionality that is required in order to be able to do the encrypted computation backed by TensorFlow Encrypted. So here we do this Keras hook by just calling sy.keras hook and then passing in Keras. And then we create a model with the same spec and load it. It's just a canonical way of sort of loading models in TensorFlow. So you create the same spec and then you can load the weights from a weights file. Now the next thing we want to do is actually launch 3 servers. Now on the previous examples, we've been leveraging sort of virtual workers for everything. But in this particular example, we're going to be leveraging TensorFlow's underlying infrastructure for being able to pass messages around quite efficiently. So these servers actually represent sort of the governance. They're going to represent Alice, Bob, and Carol, right? But we're actually going to spin them up inside of different processes instead of just running them all in this same process. So what I'm going to do here is take this first one. I'm just going to spin out 3 servers. And these could be on the cloud somewhere. These could be, on small devices, perhaps like a phone or something like that. But in this particular case, we're just going to spin up all 3 of these servers, which represent 3 different people here locally. And as you see, one is at localhost 4002, one is at localhost 4001, and one is at localhost 4000. And so for us, that corresponds to Alice, Bob, and Carol, which are at these different addresses. Cool. Now this auto feature basically means that if you are just running on localhost and you don't necessarily want to spin these up by hand, you can set auto to true and it will actually set them up for you. But just for the purpose of making sure that you can sort of see that these are real processes running in separate threads that presumably have sort of separate governance. If we were to we could put these on separate machines, on Amazon Cloud or something like that. I wanted to do it sort of separately and sort of step aside from kind of the virtual worker style interface we'll be doing for a second, just so you can sort of see what this is like. Okay. So now we're going to do the same thing we used to do before. So we're going to do model.share. This is going to take all the model parameters. It's going to basically rebuild it using secure multi-party computation and share it amongst these 3 workers, right? So now Alice, Bob, and Carol each have these 3 different, and actually Carol is the encrypted provider in this particular case. Now we're going to run model.serve. Now model.serve basically instructs these 3 workers to be ready to receive predictions as a group of individuals. Now the interesting thing to note here is that there's a lot of different reasons why Alice, Bob, and Carol could be involved in this computation. It could be that Alice is contributing data and Bob is the model owner. It could be that actually Alice, Bob, and Carol are just a model hosting service, right? So we inherently trust that Alice, Bob, and Carol won't collude with each other, and that's what allows us to do sort of encrypted computation with them. So there's a variety of scenarios that have less to do with the technology being different and more to do with with basically what's who's providing what resources and what's sort of the trust dynamic. But this particular configuration and the last demo in PyTorch as well is generic to a whole host of reasons why people would want to actually encrypt a model and data and run it. So now we're going to switch over to this one of the notebook just to show you that this is a separate client, right? So the servers are running, servers are up, model is hosted, and now we're going to take some data being from the sort of from MNIST set as well. And we're going to send it and sort of encrypt it and run an encrypted prediction against this sort of hosted encrypted server. Cool. So going to just load up the trained data set. Then we're going to connect to these same 3 workers. And we're going to send 3 images through, and it's actually going to tell us what it was classified as. As you can see, it was classified as a 7, a 2, and a 1. And so the beautiful thing here, I don't know if you saw, it's quite fast, quite performant. But what we're able to do here is have a model that we just sort of encrypt and serve. So you can see that it saw that it was served and encrypted and sent back. And this is this is basically encrypted machine learning as a service. So I gave a quick overview of why encrypted machine learning as a service is so valuable in the last session, talking about how this could potentially power sort of maybe machine translation services where the service providers don't necessarily see what they're actually translating, but they can still provide a reliable service without having to send their model to anyone else to be able to run it locally. Additionally, this can also facilitate things like where the model actually decides what to encrypt and what to decrypt. So if you think about having like an encrypted data stream and you want sort of a machine learning model to sort of decide whether something should be decrypted or should not be decrypted, and you can view this as a neural network that predicts an encrypted 0 or an encrypted 1 and then multiplies that encrypted 0 or 1 by the data stream and returns back this sort of masked version of the data stream where like most of the time it might return 0, but sometimes it would return 1. This is an example of something you're looking for, and it would sort of return that to you. So lots of very interesting use cases for this kind of technology and this kind of encrypted machine learning as a service. And of course, it's very exciting to see this propagate itself onto new platforms such as PyTorch, TensorFlow, and Keras.